Guys, this is where we were. We had points, lines, planes, circles. All good? Ready to go? We had points, lines, planes, circles, points on lines, lines of points, points of circles, yada, yada. This is the definition of a circle. Circles intersect if and only if. A point is on a circle if and only if. That's the real definition of a circle. A point is inside. Now we're saying what the interior of a circle is. And that was supposed to get us closer and closer to Prop 1.1. And your homework was, what's the next formal line in the proof? What do I mean by that? Step one, it's okay. Step one was there exists a circle that has A as the center and B on it. That's because of that. And then we obtained that circle. It's not enough to have the circle, we have to obtain it. And then step two is there exists a circle beta. We got that. Step three is that the circles do intersect. We have not justified why the circles intersect, exactly as Euclid. But now we're being explicit. We're saying sorry. Euclid could have said sorry. Step four is that there exists a pair of points. Given that they intersect, there exists a pair of points. And so what's the next line of code? So what'd you come up with? Not Sanjana.
Starts with an S.
I know.
And an A.
Thank you. Thank you. Tell me.
Sayuri.
Sayuri. I will get it. I will get it. Sayuri. Sayuri. What'd you say? You can tell me what the next part of the proof is. Oh, so great. Okay, so Sayuri is telling us next step would be create a line through C and D. Sorry, A and C. A and C. A and C. Okay, so why is there a line through something? Let's have what? There exists a line, or how should I say this? There exists a line L of type line, so that point on line AL and point on line CL. And we're going to get an error. And the error is, what's C?
Point on circle P beta and point on circle P alpha. Like I combined them.
So what we know from step 4 is that there exists a C and a D with all this stuff. What we don't yet have is that C. How do we obtain that C and that D?
So C, you don't have.
Well, how do we obtain it from the information that we have? Julio?
You just be obtained.
Obtained, yeah. So have says it exists, but that doesn't mean that we have obtained it yet. So if we obtain the point, so what's all the information that's packaged in this step? There's a C, there's a D, that C is on alpha, the D is on alpha, that C is on beta, and the D is on beta, and that C and D are not equal. So that's how many pieces of information? 1, 2, 3, 4, 5, 6, 7 pieces of information are in this one obtain. So that was what I was hoping you would do for your homework, is you would say, okay, so give me the point C, the point D, the fact that C is on alpha, which, what do you want to call that? C on alpha?
But why are those pieces of information? Are those not just bounds for C and D?
They are all pieces of information. The step 4 says there exists points C and D, so that here's a piece of information. C is on alpha. Here's another piece of information. D is on alpha. Here's another piece of information. C is on beta, and so on. So that's 7 different points of information. So let's get all of them. So we have C, we have D. The next piece of information is that C is on alpha. What do you want to call that? Let's call it C on alpha. C on alpha. What's the next one? What do you want to call that? Yeah, in what order do they come? We're going to learn that C is on alpha, then we're going to learn that D is on alpha. You see that? So now we're going to say D on alpha, then C on beta, then D on beta, and then there's one more piece of information. C and D are not equal to each other, we can call that C and ED. C is not equal to D. And we can obtain all of that from step 4. And now look at our beautiful goal state. We moved the knight, and now there's a new position of the game board. The new position is we have C and D. And we know that C is on alpha, we know that D is on alpha, C is on beta, D is on beta, and C is not equal to D. What's that?
Wait,
Which variables?
which variable and then?
I just mean that when you make a move, you see a new game board.
Oh.
And so if I just tell you knight F2, writing this is saying knight F2. But then you don't actually see what happens to the game until you look at the game board, which is this.
Oh.
This side shows you what actually happened as a result of knight F2. Does that make sense?
Yeah.
Jeremiah, tell me. You were asking something about this? No? You sure?
Yeah.
Okay. All right. Is everybody with me so far? Sayuri?
The next one. Yeah, no, but it's very equal.
C on alpha, say it again, is the next step.
C on beta. Because they're the same point.
Well, C is the same point. We know that C lies on circle alpha, and it also lies on circle beta.
Oh, so something's else.
It's already established. It's already established. From where did we get it from? We got it from if circles intersect, then there's in fact a pair of points that's on both circles. There's a point C that's on both alpha and beta. There's another point D that's also on both alpha and beta. Okay, does that make sense? And we might still have to play with those axioms until I'm trying to do something really different. Usually what we do in mathematics is I tell you what the rules are, and then we try to play with those rules. And what we're trying to do now is collectively come up with the rules on the fly that make sense for the geometry. Because that's actually, no one told Euclid what the rules were. He had to figure out what is the right way to set up my axiomatic system. And he felt that the right way to set it up was postulates 1 through 4 and postulate 5 stated the way that he stated it. Otherwise, why did he state it that way? Right? No one put a gun to his head and said, that's like a common math thing to say. I guess I should stop using it. But yeah, no one forced him to say, this is how you shall set up your geometry and now prove your theorems. In the same way, we're not forced to set up our geometry however we like. Does that make sense? So let's see. You're saying that there exists, Sayuri was telling us that there exists a line with A on L and C on L. Why is that true? What's the proof of this fact? Postulate 1. Postulate 1 was called line of points. If you give me 2 points, there is a line that has those 2 points. So that's called line of points. Copy line of points. This is by line of points, and I have to give it A and C. Okay, so let's call this step 5. Step 5, create a line through those 2 things. Now, step 5 says there exists a line with those 2 things, other than Khalil. Sim? Well, if we know that it exists, how do we obtain it? Okay. Santosh, thank you. So let's obtain. And what's the information that we want to obtain? There's the line L. There's the fact that A is on L and the fact that C is on L. So it's a triplet. So that's called let's call that A on L and C is on L. And that triplet we obtained from step 5. Knight F2, or knight, I guess F6 was the response. And this is the new game board. Cool. Okay. Why do we want to draw a line from A to C? Yeah, because we want to draw the triangle. But actually, if you think about it, what our goal is, our fundamental goal, is to prove that there exists point C so that ABC form an equilateral triangle, and the definition of being an equilateral triangle is that the distance from AB is equal to the distance to BC, and the distance of AB is equal to the distance to A. BC and AC, anyway, they're all the same distances. So technically, the way we've set up equilateral triangles, we don't need the segments. It's just about the 3 points. You could say, I mean, we could change the definition of equilateral triangle to talk about segments, but actually we don't have segments at all in our entire theory. Does that make sense? So we can get this line, but actually that line doesn't do anything for us. Like at the moment, what we've done so far, let's look at it. Yeah, okay. So I don't know why code space isn't working. We'll figure it out later. We have a point A, we have a point B. We drew the circle. We did draw. This is step 1, is we drew the circle that's called alpha with center A through B. Step 2 was to draw the circle called beta, centered at B through A. Step 3 is that the circles do intersect. We haven't justified that yet. We're building up to that. Step 4 is that there exist those 2 points. So let's draw in those 2 points. Here's the point C, and there's the point D. The fact that I can draw those 2 points is justified by our claim that we haven't yet justified that the circles do intersect. And so, Yuri, you suggested we draw the line from A to C, and we did, and we can. But actually, that line doesn't make progress towards the goal of showing that the 3 circles have the same length. So we can do it, right? The point I'm trying to make is that's a great idea. It's an idea that makes perfect sense in the way we're thinking about the geometry. But then you look at it again, you say, oh, we made a move. We brought the knight to the corner, and actually we like the knight back where it was in the center. We can just undo that move. So it's very easy to undo moves. It's hard to undo moves in chess. It's easy to undo. I mean, depends on if you're playing with someone who will let you, but there's a very easy way to undo moves in math, which is just to comment them out or delete them entirely. I'll comment them out so that they're there. Okay, so now let's think again about, here's the situation, and we want to show that the 3 distances, without necessarily drawing the line segments, that the 3 distances are the same. How are we going to argue that? Dalil and Jevin have suggestions. Anybody else? 5 up.
Wait, do we have we don't have any definition for a line segment?
We do not have a definition for a line segment, correct?
So can we make that definition?
We could. I have in mind that we're going to use something else. Is that a hand up? Yeah, that is. Anne Marie. What makes distances equal? Radii, and what axiom talks about radii? Not explicitly in terms of radii, but in terms of points and distances. In Euclid's Elements, it's postulate 3, it turns out. But how about in our geometry? In math core geometry? It's right here. It's this point on circle if and only if. Whenever you give me 3 points in a circle, if A is the center and B is on the circle, then C is also on the circle if and only if the distances agree. Let's think about what we have. We have points A, B, and C. We have that A is the center of the circle. We have that B is on the circle, and we have that C is on the circle. That will be able to tell us something about the distances, the equality of the distances. Okay, so let's try to build that up. So have, and what was that called? Point on circ if and only if. Of course, point on circ if and only if. I have to give it, what do I have to give it? I have to give it 3 points, A, B, and C, and a circle. So I'll give it A, then I'll give it B, then I'll give it C, and I'll give it a circle alpha. And what is the statement? The statement is now this. We haven't given it a name. Should I call it, I should call it something. Let's call it step 5. Okay, so this is step 5. So now it's called step 5, and it says, if you can give me a proof that that A is the center of alpha, and so on. So what's the next thing I want to feed into this? Do we have somewhere a proof that A is the center of alpha?
That is the center of that,
What's it called?
A
It's called A center of alpha. So that's the next thing I'm going to feed into. It's waiting for something. It's waiting to be fed this information. Do we have a proof of that somewhere? Yes, we do. It's called A center of alpha. So I'll feed into it A underscore center of alpha. And now the game board has changed. Now it wants a proof that B is on alpha. Point on circ, B alpha. Do we have a proof of that? B on alpha. B on alpha says that B is on alpha. You see, it's just like those 2-column proofs we've been doing, but actually formally, rigorously accurate. So B on alpha, and it's a good thing we called the hypotheses by descriptive names so that we can know what it says. So now it says point on circ alpha if and only if the distances are equal. Okay, so let me just record that. Let me just record this fact. So what I've done is I said, what is step 5? Step 5 is that C is on alpha if and only if the distance from A to C is equal to the distance from A to B. And the proof is we use this axiom. Now, do we want, so if and only if is actually 2 things. It's an if direction, it's a forward direction, and a backwards direction. We just want the forward direction. And I think the forward direction is, so let's see if we can get the forward direction. The forward direction is the first entry. If I do dot 1, so this whole thing contains 2 pieces of information, a forward direction and a backwards direction. If I do dot 1, that gives me the forward direction. Does that make sense? So let me just record that we did that. Where shall I record it? Should I keep track is it useful to have these notes to keep track of what's going on? Okay, so we started new work with step 5, and step 5 was originally this. It was an if and only if statement. Oh wait, did we do the homework? The homework is solved by writing this obtain statement, and we started new work with step 5, and step 5 was this. Okay, so I'm just recording the fact that step 5 was this if and only if. The if and only if statement, is actually a bundle of 2 statements, a forward direction and a backwards direction. A forwards direction and the backwards direction the other way around. This guy goes to that guy is the other direction. To get the first one, we add a parentheses dot 1, and that will give the first direction. In other words, so now we have the step 5 that we had worked up to, namely that. Okay, let's look at this together. Okay, so we started new work by having step 5, which is point on circ if and only if we fed it A, B, C, we fed it alpha, we fed it that A is the center of alpha, we fed it that B is on alpha. And we got that the point C is on the circle if and only if the distance from A to C is equal to the distance from A to B. So far, so good? The if and only if statement is actually a pair of statements. It's point on circ implies this distance is equal to that distance, and separately, the distance equal to distance implies that C is on alpha. That's what if and only if is. It's two statements bundled together. We don't want the second one. We don't know that the distances are equal. We're trying to conclude that the distances are equal, but we do know that C is on alpha. And so we'll use this dot one notation to say we want just the first direction. So that's what step 5 is. It's that point on circ C alpha implies the distance between AC is equal to the distance between AB, and the proof of that is this whole thing with the dot one at the end. Does that make sense? So far, so good. So now step 5 says this, and well, that's still right here it's still a function. It's a function, the step 5 that we built up so far. It's a function that takes the fact that C is on alpha, if we could prove that, and gives as a consequence that the distance from A to C is equal to the distance from A to B. So, do we have a proof that C is on alpha? Sanjana.
Points.
Where is it? This C on alpha says that the point C is on alpha. So what should I do? You guys see? So, yeah, I should add C on alpha to the end of this. Yeah. Sure, you're getting some love. I like it. C on alpha will conclude that this. So now step 5 has become that. I don't know why it doesn't draw it right. Okay, we've shown that the distance from A to C is equal to the distance from A to B, and the proof is we use this axiom, apply it to ABC. We know that A is the center, B is on the circle. We don't want the if and only if, we just want the forward direction, and then we do know that C is on alpha. And now we can conclude that the two distances are the same. Cool. Okay, so that's step 5. So we know the distance between A and C is equal to the distance between A and B. What's step 6? So in terms of pictures, we've shown that this point C, that the distance from A to C is the same as the distance from A to B. Other than Sayuri, other than Khalil, other than Vaibhav. Unless you have a question. No, you want to tell us what the next step is. Why don't we take 5 minutes and I'll leave this open and see if you can work out what step 6 is. And you can work in groups. See if you can work out what we should write for step 6.
Yeah. Wait, what does the odd do?
What step 5 does is it proves that the distance from A to C is the same as the distance from A to C. Why? Well, first let's figure out what we want to do. Let me figure out
Yeah, we want to go to the next step.
Now I want to do it.
Alright, so.
What is the last like line?
No, we got just what D and B.
I'll be right there. Sanvi? Sanvi, if you see a whole bunch of files, you click on this thing. That thing adds another file right here. Because the order that they come in is, remember what this says, it says that thing is the center. You have to tell me. And then what circle? And then you've approved that he's the center of beta. A is on beta.
Yeah.
And then. You got it. Obviously got it. Does that make sense? Got it. Well, so point on surface. The first point has to be the center of beta. This is data. A is on beta and C is on beta.
Alright, okay, scared. Yeah, you have this.
So if you want to, that's what we know. You know, this is not very high. That's what we have. Yeah, exactly. But still, Let's bring it in, guys. Let's bring it back in. So again, what we did in step, what is this called? Step 5. What we did in step 5 is we showed that AB, yeah, that's not right. I missed. B is the same as AC. And now what we want to do is prove that AB is also the same as BC. Right? That's the other direction. And instead of using, for AB and AC, we use the fact that they're both on alpha. Now we want to use the fact that they're both on beta. So let's try to build this up again. So we'll call it step 6. Abi, you got it?
Yeah, I think so. So, have step 6 and then distance with
Yeah.
AB.
So colon, so the name is step 6. Now colon, here's what we're going to prove. Distance
Of AB,
from A to B,
equals distance BC,
B to C.
colon equals.
Yep.
Point on cert BAC,
Point on circ if and only if?
yeah,
If and only if. BAC, interesting.
and then, beta,
Beta,
and then B underscore center,
B is the center of beta.
B center beta, and then, A is on B,
A is on
Point on.
beta.
yeah, A is on beta, and then 1,
Uh-huh.
and then C is on beta.
And C is on beta. Okay, so this is great. You guys had a different idea for what to do. You want to tell us what you were going to say?
So we said like the same part for the distance, like that first part.
Uh-huh.
See.
And then you were going to do BCA and use the fact that C is on beta. And then at the end, you'd have to prove that A is on beta. Now yours, there's no error message, I think. Is there an error message? There is an error message. On yours, there's an error message. On Abi's, there was a slightly bigger error message. Here, there is an error message, but look at what the error message says. Okay? What we proved here, we proved something, but that doesn't match what we claimed we wanted to prove. The reason it doesn't match what we claimed we wanted to prove is that what we proved is distance from B to A is equal to distance from B to C. And what we claimed that we wanted to prove is that distance from A to B is equal to distance from B to C.
Oh, so we just switch it.
Okay.
We can swap A and B. Yes, we can definitely swap A and B here. Let's swap A and B here, and then there's no discrepancy between what we claimed to want to prove and what we did prove. But there's something more fundamental. We're missing an axiom. Distance should be symmetric. Distance shouldn't care whether it's AB or BC. Right? Otherwise, we're going to run into trouble. Depending on which direction you're measuring it, we should have an axiom that says the distance function is a symmetric function. Does that make sense, Jim?
A separate question, how do we do half statements in a row? Shouldn't there be an obtain?
Okay, the reason we had obtains after these half statements is because these half statements, the claim was there exists something. If something exists, it exists out in the ether, and we actually want it, we want to obtain it, we want to have it here in our goal state. So the fact that it exists, it's followed by an obtain. Here, we're just saying, I claim this fact.
Okay.
I'm not saying there exists anything, I'm saying the distance from A to C is equal to the distance from A to B. Does that make sense? So that's why we don't need another obtain after this half state. This half is making a claim, and the obtain then says, give me the things that the claim says exist. Whereas this one just says, here's a fact. Okay, does that make sense? Should we add another axiom? Okay, so what we noticed, let's record what we're doing. We made, where's our place to record things? We made step 6. And this was it, and observed that there are difficulties with ordering the points in distance, which shouldn't matter. So we're missing an axiom. We're missing an axiom. What should the axiom say? What should we call the axiom? Symmetric distance or dist sim or something? Dist sim, yep. Distance is symmetric. For any 2 points, we say, how do I make a for all? I can't do it in, I can't seem to do it there. For any 2 points, A and B of type point, beautiful, distance from A to B equals distance from B to A. We should not care about in what order they came. Okay, so I'm going to add this to our list of axioms all the way up here. Let me put it next to where we define distance, just to keep them together. Jeremiah.
That work for any points now, or just for 8?
It'll work for any points. It's a function that takes up some point. It takes the point Jeremiah and Vaibhav and says the distance from Jeremiah to Vaibhav is equal to the distance from Vaibhav to Jeremiah. It'll give us a proof of this fact. Okay, does that make sense? So we've added this axiom, and now we're very, very close to the proof of proposition I.1, with the caveat that we still have to justify this, the same gap that Euclid had. So we're almost there. So now we're actually ready to work on the goal. This is the end game. We've put together everything we need, and now it's time for a checkmate. So the claim is that there exists some point C so that ABC form an equilateral triangle. What point C should we use?
The point of C.
The point C. We already have it. It's called C. There exists a point C. So we want to use C. What is that called? Obtain is a good guess. Let me write down what's going on. We are now in the end game. Prepared to attack the actual goal. So far, we've been building up our army, right? So far, we've just been building up more and more facts, but we haven't actually been doing anything about the king. So the goal is this. The goal says there exists a C, which means we have to give it some C. Obtain is if there exists some L and we know that it exists, but we want to have it. If we want to give, if the goal is that there exists a C, we want to say what C it should use. We want to specify what point. Again, this is a dummy variable. This C could be John. There exists whatever. There exists Bob, whatever. So that is equilateral triangle AB Bob, right? It's a dummy variable. So don't be attached to its name. We want to specify what point to use to make progress. And the syntax for that is it's called use. Okay, the syntax is meant to mirror the English language. Sanvi.
So A, B, and C are all points
Yes.
between like all the circles, and what is like D represent?
D is a point that we never needed. D was there because of D is the other point of intersection. D is down here,
Oh,
and we never needed D for this construction.
oh,
We just needed C. But what we said was if circles intersect, then there are actually 2 points of intersection, distinct points of intersection. We never needed D. We never needed to know that D was on alpha. We never needed to know that D was on beta. In fact, here's this. I'm teaching you too much at once. You can say, forget D. I don't need to know D. I don't need to know that D is on alpha. I don't need to know that D is on beta. And I don't need to know that C and D are not equal. And then the game board is a little bit cleaner. There are fewer things.
Yeah, I feel like you join D as well, I'm gonna prove compass.
Well, we can join D as well, and then what do you want to prove about it? I mean, we're just trying to construct an equilateral triangle. So this will construct two equilateral triangles, one for ABC and another one for ABD. Or rhombus, yeah, if you like. Okay, so let me undo all of these things, but yeah, we didn't need the point D. We're in the end game, and what did we say the syntax was? It's use. So the next thing is use what? Use the point C. So we said use the point C, and look at what happened to the goal state. The goal state has changed. to. We know what value of C it should be. It's the C that we gave it. And now we want to say that those 3 points do form an equilateral triangle. Now, I don't remember what the definition of is equilateral triangle is. It's up there. I could scroll up to get it, or I could unfold the definition. So the goal has become, the goal after use C has become this. And I don't remember what is how is equilateral triangle is defined. Let's unfold the definition. We're hiding some facts. Let's unfold the definition. The syntax for that is, can you guess? Unfold. Okay, so let's unfold the definition of is equilateral triangle. And the goal state has changed to needing to prove two things. Okay, it used to say that we have to prove is equilateral triangle ABC. I don't remember what that means. I don't know how to make progress on that. And now I do. So we need to know that the distance from A to B is equal to the distance from B to C. And the distance from A to B is equal to the distance from A to C.
So can you just use step 5 and step 6? Is that how that works?
Kind of. The syntax for that, I haven't taught you yet. Let's try to build up exactly this fact. So we don't have this fact exactly yet, because do we know that distance from A to B is equal to the distance from B to C? We know the distance from B to A is equal to the distance from B to C. But we have to use the symmetry of the distance somewhere. Let's break this into two things. In order, so we have two things to prove. Let's record. Now, after unfold is equilateral triangle, the goal state is to prove two things. So we have to prove that the distance from A to B is equal to the distance from B to B, from B to C, and the distance from A to B, yada yada. So to break those two things into their own goals, we use the term, the tactic. It's called constructor. Constructor means I want to construct a whole bunch of things together, but I want to do it one at a time. Sound good?
Yeah, so do we also need to like prove that BC is equal to AC?
Yes.
Are we gonna do that then?
Yes. We're about to do that. So watch what happens when I put constructor. This is the hard part, guys. When we get through the proof of 1.1 and we have a bunch of axioms in place and we like get a little bit of familiarity with this system, we're gonna start flying. We're gonna prove all kinds of really cool stuff in a formal way, completely rigorously. But look at what happened. Before constructor, before this line, before that move, we had one goal. You see up here, one goal. That one goal is these two things. And then I said constructor, and all of a sudden we have two goals. One goal is the first part, and then there's a whole other goal down here, which is the second part. Okay. Now, the goal state, we now have two goals. The first goal is over here, that the distance from A to B is equal to the distance to B to C. And down below, it's the second goal with all the same assumptions, and the second goal says this. With all the same assumptions, which says that. Okay, If we want to just work on the first goal and not even see the second goal, to work on just the first goal, we write the following, \dot. And I'll put sorry so that I don't get an error message. And then I'll put another \dot and sorry. Sorry means I don't want an error message. Sorry means I haven't given you the proof. So we put we write /dot, which which just hides the other goals, hides the goals you're not working on. Okay, at this point, you have to prove that the distance of AB is equal to the distance of BC, knowing everything that we know above. We're almost there. We're so close. What's the closest thing to the goal? Step 6. If we could somehow convert step 6 into the goal, we would be in good shape. So let me just copy these two things. To solve the first goal, we need to prove this. We know step 6, and we need to prove our goal is to prove this. If we could somehow convert step 6 to the goal, we'd be making progress. What do you think the syntax for that is? For that is convert. Exactly right. Convert. You guys are getting the hang of it. Okay? So if I write convert step 6, here's what it's going to do. It's going to look at step 6, and it's going to look at the goal and say, distance of BA is here. There's an equal sign. Okay, I see a pair of equal signs. I see distance of BC on the right. So that's good. That matches. But I don't know why these two things are equal. So convert step 6 is going to turn into show me why the two left-hand sides are equal. So if I write convert step 6, it converted a little too much. So convert step 6 says, oh, the distance, I see that there are distance functions here. So maybe if A is equal to B and if B is equal to A, then I can solve this goal. So we went too far in the conversion. Let's stop the conversion a little bit by saying convert step 6 using 1. Using 1 means stop at the first level of conversion. The first place where things don't match exactly, stop. And now our goal is to show the distance of AB is equal to the distance of BA. Jeremiah knows exactly what we need to do. So we wrote convert might do too much, might try to do too much. And you can control that with using. We wrote this, and the goal state became this. We're at the very end now of this part. Your homework will be to do it for the other number. The other goal is the distance of AB is equal to AC. But now we're so close. How do we finish this off? How do we show the distance from A to B is equal to the distance from B to A? Say that. Say it again. Distsim. So remember what distsim says. Distsim says that you give me an A and a B, I'll prove that AB is equal to BA. So we're at the last step. At the last step, we can give exactly the exact proof of what it's asking. Anybody know what that's called? That's called, good guess, exact. That's called exact. So if we give it exactly the fact that distance is symmetric for A and B, now it says, hey, there's an error message. you're apologizing, sorry, but there are no goals to be proved. So all I have to do is delete this sorry, and now we have a complete proof. There are no goals. We have a complete proof of the first half of this problem. The distance of AB is equal to distance to BC. Okay,